Hi, good afternoon, everyone. My name is Tsui, and I'm the host of the first ever instance of Interesting Physical Phenomena. Today's topic is the theory of special relativity. So, who came up with the theory of special relativity? It was none other than Albert Einstein. I'm sure you heard his name before. He is famous for two main things. The first being his countless contributions to science. For example, I'm sure you heard of the equation E equals mc squared before. The second is his interesting choice of hairstyle. Unfortunately, the latter will not be quite relevant to today's topics. So waves are defined as disturbances through a medium. If I drop this basketball into the pool, you will be able to see ripples originating from the point of contact. The medium in this case is the water, and the waves are behaving in a wave-like manner. So waves behave in a periodic motion, meaning that they have crests and troughs, with crests being the high points or the peaks and troughs being the bottom points. And pay attention to these two words as they're very relevant to interference. Light also happens to behave in a wave-like motion. These properties can be shown in many different experiments, including the double slit experiment. For example, say you are holding a flashlight in front of a wall. In this wall, there exist two slits for the light to pass through. So the two beams of light will pass through the two slits and produce an interference pattern on the following wall. There are two different types of interference, constructive interference and destructive interference. Constructive interference happens when the crests line up with each other and thus produce crests of greater magnitude, while destructive interference happens when the crests and the troughs line up with each other, resulting in lesser peaks. So these two types of interference patterns can be seen in the interference pattern on the right side. The points of greater intensity are a result of constructive interference, while the points that are darker are a result of destructive interference. Thus, we conclude that light also has wave-like properties. All waves pass through a medium. If space is largely a vacuum, how can light exhibit its wave-like properties? Thus, scientists have long believed that there exists a luminous ether through which light permeates, such that it can exhibit these wave-like properties. However, in 1887, the Michelson-Morley experiment returned a no result, meaning that the hypothesized luminous ether did not necessarily exist. This, in conjunction with the problems between Newtonian mechanics and Maxwell's equations, caused Einstein to propose his theory of special relativity in 1905. Einstein's case rests on two main concepts. The first is that the laws of physics are the same in all inertial or non-accelerating reference frames. The second is that the speed of light is constant in a vacuum, no matter your reference frame. Let's quickly review relative motion. On the left, we have me. Let that be inertial reference point 1. On the right, we have the Pokemon Dragonite. He is stationary. He's going to be our second reference point. In the first instance, we're walking across at the speed of 2 miles per hour. In the second instance, I'm going to walk across again, this time throwing the stuffed animal in my hand at a relative speed of 3 miles per hour. Thus, from the perspective of me, it's moving at 3 miles per hour, but from the Dragonite, we would add together their true speeds, resulting in a total velocity of 5 miles per hour. Now let's consider a similar experiment, except for the two objects are moving at much higher speeds. So right here we have Darth Vader in a spaceship that is capable of moving at half the speed of light. Attached to the spaceship is a flashlight, and light goes at the speed of light relative to it. Okay. My mouse will be the second reference frame, which is stationary. So as Darth Vader's speed proceeds, relative to his spaceship, the light is moving at the speed of light. Following the previous logic, we would add the two speeds to determine the relative speed towards the stationary mouse, resulting in a final result of 1.5 times the speed of light. However, this is false, as we have done numerous experiments that have proved that the speed of light is constant in all reference frames. Thus, how can we solve this issue? The answer is time dilations, or that An object in relative motion to a stationary clock will experience a different flow of time compared to the stationary clock. Let's do a quick proof on how the time dilation expresses the differences in time between an object that is in relative motion to a stationary reference point. Okay, so here in the plane we have Anakin Skywalker. The plane is moving quite fast, and you are on the right on this Earth, and you're currently not moving. Anakin Skywalker is holding a light clock, and we're going to refer to his time as t and your time as t prime. The distance that the light beam travels between the two mirrors is going to be d. So in one trip, the light travels the path of 2d. So we can set up this simple equation and determine that t equals 2d over c. However, from the perspective of you on Earth, light does not take the same path. So during t prime, your spaceship travels a distance v times t prime. Each half is equal to v times t prime over 2. The distance that light travels, however, is equal to the hypotenuse of the triangle, or the speed, which is c, times t prime over 2. We can now apply the Pythagorean theorem on this triangle and get an equation for t prime in terms of d, v, and c. So we're just doing some basic math right here, and then we're going to rearrange the terms such that t ends up on the left side and d ends up on the right side. Okay, now we're going to do something tricky. After taking the square root of both sides, we're going to pull c out such that we are left with the equation in t prime equals 2d over c times 1 over square root 1 minus v squared over c squared. Do you notice anything familiar? Yes, that's right. 2d over c is equal to t. So we're going to substitute t in for that, and we're left with t prime equals t times 1 over square root 1 minus v squared over c squared. The part on the right is known as Lorentz factor and has many importances. So what are some takeaways that we can get from this equation? So on the right portion, when we look at v squared over c squared, that means that as v gets closer and closer to the speed of light, v squared over c squared will approach 1, which means that t prime will be much, much greater than t. In other words, the faster you move, the slower your time will flow. Now let's move on to length contraction. So length contraction states that the length of a moving object is actually less than its proper length, or the length measured when the object is stationary. This is necessary to compensate for time dilation and is only measured in the direction of its movement. Furthermore, while length contraction exists at all speeds, unless you are traveling very close to the speed of light, the length will not be noticeable to the eye. The general formula for length contraction can be easily derived from the formula for time dilation, using the equation distance equals rate times time. We get that the contracted length is equal to the original length times 1 over the Lorentz factor. Now let's wrap things up with the ladder and barn paradox. This is me in front of a garage. This is me with a long pole in front of a garage. This is me attempting to run fast with a pole across a garage. For the purpose of this experiment, let's assume that the length of the pole is longer than the length of the garage. Would there be any point in time where I'll be able to fit the whole pole inside of the garage? According to length contraction, from your point of view, the length of the pole will appear shortened the faster I move. Thus, you would believe that I would, in fact, be able to fit inside the garage. However, let's consider the perspective of me. I'm stationary, but the garage is moving towards me at very high speeds. Thus, the garage would be appearing quite short, and how would I be able to fit inside the garage? In order to answer this paradox, we need to consider the original idea simultaneously. Okay, we're back here with Anakin Skywalker and his spaceship. We're going to use him to show the example of the train moving at a high speed, where lightning strikes both the front and the back of the train. Okay, so from your perspective, the train or spaceship is moving towards you at a really high speed, and both lightning strikes the front and the back of the train at the same time. However, from his perspective, he moves towards the first lightning strike, so the first lightning strike will actually appear first than the second lightning strike. So thus, while you see both of the two lightning strikes at the same time, he'll see the first one first before seeing the second one. So going back to the original question about how I can appear to show the fully fit inside of the garage with a pole from your point of view? The answer is, from your point of view, both ends of the garage appear at the same time. So no matter what, since of lump contraction, there will be a point where I'll be able to fit inside the garage. However, from my point of view, there's obviously no way that I'll be able to fit inside the garage at the same time since the length of the garage has contracted, right? So this all goes back to the idea that there's no true simultaneously. From your point of view, both ends of the garage appeared at the same time, but from my point of view, the first end of the garage appeared first and disappeared before the second end of the garage appeared and disappeared. Thank you for spending your time watching this video. See you next time. Bye bye.